if you missed any interesting seminars on YouTube or if you want to revisit them. And that gets me to today's speaker. So we have Professor Warren Poole. He is a professor here in the Department of Materials Engineering on the Vancouver campus. He holds a Canada Research Chair in Through Process Modeling of Advanced Structural Materials. He is also the Rio Tinto Aluminium Chair in Materials Process Engineering, and he is a fellow of the Canadian Academy of Engineers. So he's been a longer-term seasoned professor here in the department, and he will talk today about using instrumented indentation and 3D EBSD to study plasticity in magnesium alloys. And with that, I hand over to Warren. Thank you.
Okay, thanks, Annette, for that very kind introduction. So thank you for the opportunity to make this presentation today and maybe introduce a few of you to some of the new techniques that we have here, some of the equipment that we've gotten over the last few years. So let me, okay. Now I'm stuck. There we go. Okay, so the first thing to do is to acknowledge the people who actually did the work. So Shuheng Li is at the back there. So she's just finishing her PhD, and most of the results I'm going to show today are from her, but she had a really nice collaboration with Ruth Birch here on the 3D fib sectioning, which I'll come to later, to look at the microstructure. And Ben Britton, who's a co-supervisor of Shuheng. Okay, so why magnesium? I'm sorry for the online people, but I want to pass around these two cars, or models of cars. One is made out of steel, the conventional material that we have, and this one is magnesium. So that's kind of the major motivation for the work. Magnesium is 80% lower in density than steel. So it's all about lightweighting of vehicles. But magnesium is an interesting material. For maybe more than 50 years, people have been saying it's the next great material, and hasn't quite got there yet, but we're making lots of progress in this area. Okay, so I did just want to acknowledge the indentation system and the plasma fib are both investments by the Canadian Foundation for Innovation. Okay, so let's talk a little bit about magnesium. So I brought a little unit cell. It's hexagonal, close packed in crystal structure. And this is kind of the source of the problems that we have in magnesium. But we'll start off. The first thing we'll see is that the material is almost elastically isotropic. So that just means if you push elastically in different directions, it behaves pretty similar. So not all materials are that way. So it's a good thing which we'll take advantage of in our approach to this. And the Young's modulus of magnesium is around 45 to 48 gigapascals. And it doesn't change too much, as I said, depending on which. But the plastic response of the material, and this is where the challenge has really come. If you think about a car, you need to form the parts, like a hood or a bumper. And then maybe you're unfortunate, you're in an accident, that car needs to absorb energy through plasticity. So the anisotropic response of magnesium comes about fundamentally related to the crystal structure. And here we're just showing some of the slip planes and slip directions. So plasticity is dislocation mediated. But we'll see there are some other mechanisms that can come in here. And the problem is that slip in the basal plane is very easy. We'll see the resolved shear stress to cause plasticity in this direction is very low, just 1 or 2 megapascals. But this doesn't allow any deformation along what we call the C-axis, right? So the basal plane is characterized by its A dimension. And this red plane here, the hexagon, is the basal plane. And you can see these are very low resolved shear stresses. But this green plane is second order pyramidal, it's called. And you can have slip of dislocations on this plane, but 40 to 50 times higher in terms of the resolved shear stress to activate that system, at least in pure magnesium. And then finally, there's one other way in which magnesium often deforms by mechanical twinning. So different deformation, which involves a shearing of the crystal and a rotation of the lattice. And there's some plastic strain that is associated with this deformation twinning. So that's where we start. So the motivation of this study is to extract information on the temperature dependence of these properties, particularly deformation in the c-axis. So the height of this hexagonal prism. And we also want to look at alloy additions. Can we modify that ratio by making different types of alloys? So what we're going to do is we're going to take a polycrystal, and I'll sort of walk you through the different steps of this. We're going to choose a grain of a certain orientation, and then we're going to do this as a spherical tip, and we're going to go into this grain, and we're going to probe the material and measure its response. Over here on the right is just some literature data. It's very difficult to measure some of these parameters, but what they're trying to show you, this pyramidal slip, which was around 40 megapascals versus the basal slip, 1. As you go up in temperature, this drops down substantially, okay? So we'll see if we can get some information from these indentation tests that are consistent with this. Okay, so indentation, probably more than 150 years, people have been doing indents to measure the local properties of materials. And from an engineering point of view, there are different scales: Brunel, Vickers, Rockwell, hardness. Some of you may be familiar with those. And what I'm trying to show here is you can use different tips. So a Vickers indenter uses a four-sided pyramidal indenter. It's actually quite flat. This angle here is, I think, 109 degrees. But you're pushing that in, and then you're going to have a square residual indent. You can have conical indenters with a sharp tip, but we're going to focus on a spherical indenter, and I'll try to explain in a minute what some of the advantages are of using the spherical indenter. Basically, we want to avoid the singularity at contact between these sharp pointed indenter tips. And in instrumented indentation, basically we have a load cell and a displacement measure, and we're going to push the indenter tip into the sample. We can program in a closed loop system, load versus time. So in this case, we ramp up the load, we hold the load, and then we unload it. And the output that we get is something that looks like this: load increasing and then decreasing on unloading. So we'll try to extract as much information as we can from this type of, that's the raw data. Here's the machine. So it's in this building down in room 63. So this is a Brooker Hisotron, and this is a vibration chamber or anti-vibration isolation system here. And then this is the system here. We have a stage. You can put your samples on. They can move in X, Y, so you can move around, do indents at different locations, different samples. You have an optical microscope so that you can see where you are on the surface if you want to position your indent in a certain position. There's we have two different, in our systems, two different load transducers. So the standard one has a maximum load of 14 millinewtons. So very, very tiny loads, right? And the larger one goes up to 0.3 newtons. This is the system, and then there's a whole bunch of electronics in the bottom for controls. So I thought I'd just say just a little bit about how the system works. And there are a number of companies that make these systems, but basically we have a plate with a rod on it, and then we're going to attach our tip to this. And the plate is suspended on leaf springs between two outer plates, the bottom and the top plate. And if you apply a DC voltage, there's a capacitive drive of the plate downwards, okay? And so you can see here it's moving down, and then we measure displacement by high frequency voltage that's across the outer plates, which measures the difference in capacitance between here and there. And then these are calibrated against known standards. So we'll be able to get load. And the system is primarily a load control system. So most of the tests we run are in that mode. You can do a quasi displacement feedback system, but that's an indirect control mode. Okay, we're going to talk about these tips in a minute, and the fact that we can do the indent at room temperature, that's kind of what normal that you might expect, but we also have a heating stage. So you can go up to 400 degrees Celsius, and I'll show that in a minute. But we have different tips for low load, 15 millinewton, and the large load. And these all, in these cases, they have little spheres at the end for the indenter shape. And they have different radii, 5, 10, 250, or 50, 250 microns in radius. So we have, for each of these, 4 different tips. And then you can, depending on the load that you need, and then these longer tips, I'll show you in a minute, these are on quartz tubes. They go through into the heating area and then allow the indent to occur in the hot zone of the nano indenter or the instrumented indenter. Now we start off, each of these tips has a different compliance. So we have to always, we're measuring the overall displacement in the system. So that includes not only the displacement into your sample, but the displacement of the indenter and the tip holder. So we have to do calibrations on all that. Then we come back to this question of why would you use a spherical tip? Well, the beauty of a spherical tip is that it follows Hertzian elastic contact. And we have equations that describe the force versus the displacement of the material as it's going in elastically. And we can also define, I'll show you later, the entire stress field underneath the indenter. Now, this is the case where, because magnesium is nearly elastically isotropic, these equations, these analytical equations that Hertz derived maybe 150 years ago, can be directly applied. So you can look at other materials like zinc's hexagonal. It has a very anisotropic elastic modulus dependence. So this approach would not work as well there. You'd have to do a more detailed analysis. Okay, so just one general point here. This is not really central to the talk, but I did want to point it out because, you know, often we buy things from suppliers and they say, okay, this is, in this case, they told us this tip was 10 micron in radius. Okay, and we did a bunch of tests and Xusing was pulling her hair out because they were not consistent with the 5 and the 50 micron. So we went back and we did indents on, they give you a fused quartz sample, which is an amorphous material, which has isotropic elastic properties. Its modulus is known at 70 GPa. And so we did contact, elastic contact, and we basically varied the radius until we got a match. And it turned out that this tip was actually only 7 microns in radius, not the 10 quoted by the supplier. So always check. But, you know, I'm giving an example of the extreme. Most of our tips were pretty good within, you know, 10%. But again, just always check. So the next thing, you know, you think about it, some of our tips are very small, like 5 microns, right? I mean, what, your hair is something like 70 microns. So these are very tiny tips. And an important point is, when do they actually contact the sample? So tip is coming down, when does it actually touch? And the machine is quite smart about these things, but it has a two-step process. So the tip comes down at 0.1 micron per second. It reaches a set point. It actually will plastically deform when it first comes down. It's actually coming down, even though that's a small number, relatively quickly. And then it's going to crash into the surface, make a deformation zone. But that's going to give the machine an idea of where the surface is. So what it's going to do is then it lifts up half a micron, 500 nanometers. It moves over. You can specify how far it moves, 15 microns we did in this case. And now it's going to come down, and it knows where the surface is. So it's going to come down very slowly, and we'll have a very gentle and nice contact with the surface. And then the indentation data starts. And of course, we've left this deformation zone. We've moved far enough away that it won't affect this measurement. The next problem you have is, when did you really make Hertzian contact? The surface won't be perfectly flat. It'll have some undulations and things from contact. So a lot of work has gone into determining where the true contact point is here. And Shuheng did a lot of work on this and doing different types of regressions and analysis of determining, when the true contact load and the displacement, any offsets that we need to apply to the data. And the results are actually relatively sensitive to getting this first contact point well defined. So this group at Georgia Tech, Surya Kaladindi's group, has done a lot of work in developing how to convert the raw data, so load displacement, into something like what we'll call an indentation stress strain curve. Okay, so that's at first it seems like a clear analog to like a tensile test, but we'll see it's a little bit more complicated to make the relationship. But if you want to calculate stress, it's the load over the area. So that's the sort of normal definition. The key here is, though, you need the area. So it's really clever. The people who designed these, Oliver and Farr, back in the mid-90s, I think, so a long time ago, they came up with this idea, again, as computers and control systems developed, that in fact, rather than just going up linearly in load, we're going to superimpose a small sinusoidal loading function. And the displacement in this would just be like, a few nanometers. So we're really tiny things. But it's like you're coming down and you're oscillating. So you have a little indentation stress strain curve each time. And from the unloading curve each time, the stress goes up and down and up and down. Well, you can look at our stress or the displacement and load. Are they in sync? So if you do polymers or something, there can be a lag between them and you get a phase shift. But in metals, they, at least at this case, at room temperature, low temperature plasticity where there's no creep, but you can determine from these unloading curves and the mechanics if you know the Young's modulus, which we do in this case, it's magnesium, from the unloading stiffness, you can get the area as a function of displacement. So once you know the area, then you can calculate the stress. So you can get Young's modulus if you don't know that, but then we'll look at yield stresses and the hardening of the material under the indenter, and you can see this is the type of curve you'll get. So you're in an elastic region, you'll have the onset of plasticity, and then in this case, we'll see some discontinuities that can arrive from different things, which I'll say a little bit more about in a minute. So again, this is some analysis that Shuheng's done. In the initial portion, we fit Hertz to the data, and it fits very well. So there are no adjustable parameters here. It's magnesium, the Young's modulus, the shape function of the tip, and you have the Hertz solution. And then she basically defines a deviation. So the black data is the experimental and the red is Hertz, and some deviation point where the load deviates from the elastic solution. And over here, this is showing you the stress strain curve after you've done these calculations. And this is the yield point. Turns out that this region here in the magnesium is very steep. So it really depends. You can change this yield stress from like 100 to 150, so 50% change, depending on where you define the onset of plasticity in the material. And again, I just point out, remember, this whole analysis is premised on the fact that magnesium is nearly elastically isotropic. Okay, the next question you'd say is, well, what grain do I want to select? I have these grains all in different orientations in a polycrystal. And we can look at some earlier results from my previous PhD student, Gazelle Nayeri, and she did indents. So here you can see nearly parallel to the c-axis, so this way. And then this green one is nearly parallel. We call this the prism plane, or perpendicular to the prism plane. And then she looked at a case where this was at some angle here. So we'll look at the indents. So this is the first case. And what we see are these blue things here, which are twins. So it's when the crystal in magnesium, it flips 86 degrees when the twin happens. Okay, so in the Poole figure, you can see from the initial orientation in these twins, the orientation is rotated out to the edges. And in principle, there are 6 variants of these twins, and sometimes you'll see, in fact, 6 different twins that have formed. And these twins form outside of the indent. So these are indents at different depths of indent. And you can see that initially you don't see twins, at least post-motor, after the indenter is removed. And then you start to see more and more twins, depending on how deep you go. And these are the 2 other cases here. This is for this case, so indentation perpendicular to the prism plane. It's actually more complicated, and the twins come about earlier. And sorry, the bottom one is for this case where you're sort of at the crystal at something like 45 or 50 degrees to the indentation axis. And again, now you get asymmetric deformation, right? Because you can imagine as your indenter's coming in, it just sort of pushes down the side of the crystal. So taking this all into account for a number of reasons, maybe I won't go into too much detail, but this is a nice geometry to look at because you're wanting to, fundamentally, we'd like to get a mechanism for deformation along the c-axis. So if we do the deformation parallel to the c-axis, maybe we'll get some information on that. So that's what Shuheng has done. A little bit on the heating stage. So there's 2 parts to the heating stage. Goes on the stage in that indenter system. And this is the little heater down here. And there's water cooling. And then this is the top plate. So this goes on top of this, and then it clamps down. And you can see there's a little hole in there. So that's where that quartz tube with the indenter tip goes through to do the indent. And there's the indenter there, right? So this is something like, I don't know, is it 20 millimeters or 15 millimeters in length? Something like that. Just a quick thing on a test that Shuheng did at the beginning. These are different indenter radii, load, unload, and you can hardly see it here, maybe a little bit better in this one. There's sort of a dark purple and a light purple. So these are done initially on the sample at room temperature. Then we heated the sample up and held it 1 hour at 100, 200, 300, and then cooled down. And during the test, we had high purity gas passing over. So we didn't, and we wanted to test, was there oxidation of the magnesium? Because clearly if I had an oxide film and I tried to indent, that would affect things. And you can see that there's almost no difference. This 250, there's really no difference of the heating cycle. So the protective gas has worked quite well. There'll always be some very thin oxide on the material, but it didn't grow excessively, or it didn't affect our measurements during the test. Okay, so let's look at our workflow. So someone's going to give you a material. We'll look at some commercial pure magnesium, some alloys. This material was annealed to grow the grains larger. Then we did an EBSD map to measure the orientation of the grains. And then we chose a grain, and then we do indents in it. This red grain here is a grain where it's more or less close to being the c-axis is perpendicular to the surface of the sample. So then different radii and different temperatures. So 4 different radii of tips and 4 different temperatures. So this is the raw data, load displacement. The bigger the radius, the harder it is to push in, right? So the loads are higher. So this is where we have to switch from the low force to the high force transducer. This is showing you for a 5 micron tip what happens as you go up in temperature. So always have the elastic region at the beginning, and then you can see quite significant deviations at 200 and 300 then from the low. And then these are these indentation stress strain curves, if you like. And what they show is, you know, here we yield, and then there's a lot of hardening in the material, but at 300, it's almost flat, right? So very little hardening. We can get other information. Again, this is Hertz, and you see the deviation occurs quite low, but this is maybe 15 nanometers of depth. So again, just to emphasize, we're doing very local, small-scale measurements, but we'll see these discontinuities. And these discontinuities can, I won't go into great detail, but they can arrive from 2 different sources. First, if you indent a small enough volume, there may be no dislocations. It may be a perfect crystal, so you may have to nucleate dislocations in the region. Or when you get these twins, when it flips side, that happens as a burst. So that affects the load displacement curves, and then it shows up in the stress strain curves. So a bunch of equations. I told you these are the Hertz equations, so enough of that, but just to show you that they exist. And what that allows you to do is, for a certain orientation of crystal, it allows you to resolve. So maybe just one thing. So you have, you know, different components. You have shear stresses, radial. This is in cylindrical coordinates, hoop stresses, and tangential stresses. And they're spatially varying underneath the tip. So what this is showing you is the resolved shear stress from that 3-dimensional stress tensor onto the basal plane. Okay? And so the basal plane would be horizontal here. But even though you're pushing down, there are regions where the material is being pushed sideways. So that's one way actually to think about. It's kind of a little bit like a snowplow coming in. It wants to push material to the left, or to the right, sorry, and to the left. So you can calculate how much shear stress is resolved onto the basal plane in the direction of the Burger's vector. And here it's about 0.35, this indentation Schmidt factor, if you like, of the yield stress that you've measured from the indentation stress strain curve. And here's a plot of the resolved shear stress as a function of indenter radius, which, a couple of things here. There's a large scatter in the data here when the tips are small. This is 5 micron, and very little scatter when the tips become larger. And there's a large dependence of that stress to initiate plasticity on the size of the indenter tip. And this is well known. We didn't discover this. It's called the indentation size effect. So as I said, large scatter in here. So, again, we think this is actually a real effect, that there is generally a stochastic nature. And again, that's going to be related to the size of the indentation stress field under the indenter. So when the tips get small, there may or may not be any dislocations in the stress field. And if there are none, we're going to have to nucleate, and the stress will be very high. And then as the field of the stress gets larger by using bigger indenters, the probability that you find dislocations in there becomes greater. And once you reach a certain size, right, it's like a continuum that it behaves like out here with very little scatter in the data. So again, I won't go into all the details here, but Shuheng's developed a model using Weibull statistics to look at the probability of a dislocation or a set of dislocations being in the indentation stress field. And then she's been able to come up with a probability of dislocation nucleation. So if the indenter is large, you don't need to nucleate. And if the indenter tip is very small, you do need to indent. And then that allows to calculate at a very large radius what the critically resolved shear stress is. And what I like about this, first of all, it's about 1 megapascal. So that agrees with what single crystal bulk measurements are. Whereas if you look at like some of these numbers here, they're like 250 megapascals. Like that's a long ways from 1, right? But once we take this size effect in, we get numbers that agree very well with the literature. And it's essentially temperature independent because basal slip is so easy, thermal activation of basal slip is not a consideration. Okay. So the last thing from the bulk curves is this is looking at how the indentation stress strain curves vary, 5, 10, 50. Let's maybe focus on this 250. So again, the actual elastic portions down here, and then you can see that the hardening during the indentation test varies with temperature, right? So this is 300, 200, 125 degrees Celsius. So we have some measure of the relaxation of the stresses in the material during plastic deformation. And then you can start to look at alloys. This is just one example. I've actually been reading through Shuheng's thesis this morning, the chapter on this, which is looking quite nice. And she's done a much more detailed analysis. But here we plotted magnesium with just 0.1% calcium. The literature says calcium changes things about the dislocation core and things. And you can kind of see here, this is the magnesium curve, or the magnesium calcium is in black. And then this is at 100 degrees and this is at 200 degrees. This black curve it's kind of similar to magnesium at 100 degrees. So, and she's done a lot of measurements to show this trend follows up, that calcium behaves like at room temperature, it's like you're doing the deformation at a higher temperature in commercial purity magnesium. Okay, so how am I doing for time? Hopefully a couple minutes. So now what the heck's going on in the material under this indenter? So this is where when we got the plasma fib, that capability came about. Okay, so what we're showing here is, so this is the hunk of magnesium, right? This whole thing. Hopefully you can see there's the indenter, it's spherical, right? And we're basically going to do a chunk lift out, right? We're going to use the xenon atoms to machine away, and then we're going to cut off the sample. We're going to lift it out, and there's the indent. And now we're going to section this material with the xenon, like a loaf of bread, and then reconstruct the 3D microstructure. And this is just one image here. You can barely see it. I'll show you some examples in a minute where it's much clearer, but you can see some from the pattern quality. This is an EBSD measurement. We can see some features beneath the surface, okay? So we should have isolated the entire indent, and then we're going to look at what's residual left behind after the indent was done. So we start on the surface. So there's your indent. And you can see these little twins, as I said. I think in this particular case, at room temperature, again, remember this is flipping by 86 degrees. And there's at least 5 of them here, of the variants. I'm not sure if there's really one here. And then this is in 3D. So we've reconstructed the twins and separated them from the material that's untwinned. And you can see there's 1, 2, 3, 4, 5. There's 6 of them there, as you'd expect from the symmetry of the crystal. And the Shuheng's measured the volume. I think she has some more refined measurements than these ones here. But at 200 degrees, we only see 3 major twins, and their volume's larger. So that's the first thing that we see. And of course, the load displacement, these were done to the same displacement or near the same displacement. And of course, the load to get to that displacement is much less at 200 degrees than it is at room temperature. So in this case, the angle between the indentation direction and the c-axis is 3.6 degrees, very close. The load's about 1.6 times higher at room temperature. And we see these different number of twin variants and the volume of the twins. So I just put this slide in just again, maybe to get us thinking about, this is a very simple upper bound solution for what happens during indentation. You're pushing a block of material, in this case it's a square cylinder, not a circular, but the idea is the same. You're pushing this material under the indenter down. It spreads sideways. So in this case, the spreading occurs by slip on the basal planes. And then it can move upwards and out. And we can actually measure this material that's displaced under the indenter. You can see they call these pileups around the indenter. Okay? And this material can move up by, don't need to worry about all the details. These are 101 bar 2 extension twins, they're called. So when we look at the surface, we see these twins that are surrounding, and they're coming about because the material is being pushed in, it goes up, and then it flows up to the surface. Now, what's really interesting is if now you do a cross section. So this is at the center of the indent. So the indent is here. These are the twins up here. But look at this features here. So there's this very sharp wall. And the orientation of the crystal in these underneath the indenter, it changes as you go from left to right. So the blue on each side is the initial orientation, and then this is a plot of misorientation. So if you look at line 1, you go along, nothing's happening, and then it shoots up to 7 or 8 degrees. So the crystal is literally rotated from where it was initially, and then it comes back. If you go right down the center, no change at all. And then if you go to the other side, it flips in the opposite direction. And then again, there's a very sharp wall. So this is what we see, and I think this is going to be a movie now, starting at the surface and slicing, looking down into the material, okay? And misorientation, so the large misorientation is red. So this looks here in this static image like a donut, right? It's got a hole in the middle that's blue, which is the same. And let's see if we can get that to play. So we go through those twins, and then the donut, as we go down, and the donut gradually disappears. Okay, and then at the bottom one is, we see similar things at the high temperature. There are bigger twins, But again, you see this donut. But the depth of the distortions or misorientations, whatever you want to call them, is much less at 200 degrees than it is at room temperature. If you look at this, this deformation field is like 5 times greater than the diameter. The material is really being pushed in, and we'll see that we can interpret these misorientations as arrays of dislocations. So those ones that are pushing like the snowplow out, but they have this very strong barrier because the stresses drop off very quickly when you get outside the contact point of the indenter. So if you're into fancy crystallography, this is just showing you the rotations on a Poole figure. And you can see what these are is like, they're like rotations like this. This is the center of the rotation, and then it's moving around there. And there are two main directions. Don't worry about those. There are certain crystal directions, and it's a combination of these two which make up these rotations. And in fact, if you look at these rotations, again, we've got a movie here. So blue is 1 bar 1 0 0, and green is 1 bar 2 1 bar 0. Slight difference between this green and that green, but don't worry about it. But what you see is there is six-fold symmetry here, again related to the crystal structure. And the blue are rotations around 1 bar 1 0 0, and the greens are around these other two. So let's see if we can, again, we'll take slices from the surface moving down into the material. So again, it's actually really beautiful. My colleague, Chad Sinclair, I guess about 10 years ago, he predicted what these rotation axes should be, and then we did the experiment to show that he was right. So not that often that we predict things and then find them to be true. So that was, again, the top, and here's the bottom. And again, you see the same thing. These are, there's only blue and green. These are special rotation axes. And as I don't want to spend too much time on, but they're related to the close packed directions. So these are the close packed directions in the crystal, and this is the 1 bar 1 0 0. So you can make up dislocation arrays that pile up that will give you these rotations. And this one's made up of a combination of two different types of dislocations to give you that rotation. So just to kind of summarize the view of the indentation. So the spherical indenter comes down. We have these twinning systems. We have the basal slip, comes down. This is the indentation Schmidt factor. So these are the regions where there are large stresses, again, pushing to the left and to the right. So these dislocation loops are going to expand in these regions. Right underneath, it's, you're pushing down. There is no resolved shear stress, so no dislocations in the middle here. And then you see arrays of dislocation loops, and they give you these rotations that we see as we go from this wall. And the last thing we'll talk about, what's going on in the wall, okay? Again, there's a lot of detail here, but I just wanted to try and give you an idea that everything works out here well in terms of the crystal structure, the dislocations that are moving, and the rotations that we measure. And again, I won't show you this. This is just where we rationalize the different rotation axes. So let's come back to the wall. So this is the last part. And we're going to focus on these walls here. So we'll do a different type of analysis called a weighted Burgers vector analysis. So you can calculate in different directions. So X is horizontal, and Z is vertical in this description. And we can look at spatially, what amount of Burger's vector do you have? What component of a Burger's vector do you have? And if you look here, we really don't see very much, right? We don't see all the details of these arrays of dislocations. But what is worth focusing on is in these walls here, which are yellow here, you see big spikes. And they're indicating, the way to interpret this is that in these spikes, you have components that are in the c-axis. So that was the problem if we go right back to the beginning. How does it deform in the c-axis? And so it seems in these walls that we are producing dislocations, like the second order pyramidal ones, that are not easy to activate. And we see evidence that there's a component of the Burger's vector in the c-axis in the walls. So it'd be interesting. There is one paper where people did TEM under a similar material and loading condition, and they did find, they were able to do a G.B Burger's analysis and find these C+A dislocations. And just to show you, this is the high temperature case. Again, just confirming that the deformation field goes less deep. And the way I would think about it is that you're pushing this material into the material and it wants to relax, but it doesn't have any mechanism to do that at room temperature, or very little. It's hard to happen. Whereas at 200, it's much easier. So now the material relaxes. And in like the depth of penetration of the material you're pushing in is much lower now than it was in at room temperature when you go up in temperature. Okay, so now I'll just summarize. So why is this interesting? No need to grow a single crystal. There are people in this building that grow all kinds of high temperature superconductor crystals and things. That's hard to do. You can screen alloys with minimum material usage and get the yield stress and the indentation hardening. You can look at different temperatures. We could look at multi-component alloy compositions. This enables a rapid assessment. So you could make a diffusion couple, for example, where you had pure A and pure B, and then you allowed the atoms to intermingle, and then you could look at how does the indentation response vary across the compositional gradient. And then the PFib-based 3D EBSD really opens up a window to look into how the deformation's actually occurring in the indenter. I guess my last comment will be this PFib, collecting this data, I think took about 5 days of data collection. So it is a big experiment to do, and there's a lot of data to analyze there. So they have to choose your experiments carefully. So with that, I'll close off, and I would be happy to answer any questions or any comments.